All right, good morning, everybody. Welcome to our science seminar for this week. Okay, great to see you. Note that next week, if you come here on Thursday, there won't be anybody here. But next week is what? Spring break. Yes, so I know that you'll all be wanting to come here Thursday at 11 because you're being conditioned to do so. But you know, take the week off and do something fun. Yes, you know, don't work all the time. Just most of the time. That's what we teach you to do, right? Yes? No? Okay. All right. Today we have with us Dr. Lynam, who's a chemical engineer from Louisiana Tech, which is a famous chemical engineering school. So, you know, she comes from the School of Chemical Engineers, so if you want to hear about chemical engineering, Louisiana Tech is the place to go to find out about it. Yes, fun place to visit there. Dr. Lynam has her Bachelor's of Science in Chemical Engineering from Case Western University over in Ohio. Then she moved over to Nevada, where she got a Master's of Science in, what do you think? No, not chemistry, but chemical engineering at University of Nevada in Reno. And then she liked it so much there in Nevada that she stayed on and she did her PhD in, what do you think? Chemical engineering over there at University of Nevada in Reno. And from there, she went to Louisiana Tech, where she is now the program chair of, what are you, the program chair of chemical engineering?
Yes,
Yeah.
yes, sir.
So
Yes, sir.
not only do you, so top dog coming in here to talk to you guys about chemical engineering here. So pay attention to what's going on. She has opportunities for you guys to do research in her lab. She's looking for graduate students, and she's going to pay you guys a whole bunch of money, right, to come.
Yeah, usually you can get funded.
Yeah, you usually get funded.
Yeah.
So if you're looking for careers in chemical engineering, whether you're an engineer or a chemistry major, this is the talk for you today. So let's give Dr. Lynam a warm welcome.
Thank you very much. Well, I must say that being a program chair and trying to deal with a bunch of professors, it's a lot like herding cats. Just so you know. And the other thing I want you to know is my name is Dr. Lynam, like line them up against the wall. Okay? He was saying the other one, which we won't repeat. Anyway, so I'm Dr. Lynam, and I do stuff like this. I convert things that are waste into products. That's kind of the main thing I do, and I do it an awful lot with biomass. Who knows what biomass is? Organic materials, that's right. Woo! All right, who said that? Okay, you get a sticker. Big sticker. There you go. All right. Lots of people like to put these stickers on their laptops. That's typically what students do with those. Anyway, okay. So this is just kind of what's going on here. I'm trying to take things that are biomass, that are organic materials. So can you point to something in this room that is not biomass? Metal, right? And metal is inorganic, and so it is not biomass. But there are a lot of things that are biomass, and I'm mostly into things that are like waste biomass, okay? So I'm not interested in taking corn and turning it into ethanol that you put in your gas tank. I'm interested in taking other things like pine needles maybe, or rice husk, that sort of thing, and making it into a biofuel or a different kind of product. Okay, so my story is I am from Reno, Nevada. All right, so when you think Reno, what do you think? Gambling, yeah, casinos. Of course, I'm not interested in that. That's just, it's not very interesting to me. So, but that is where I first got interested in biomass. But Nevada is kind of a place where biomass is not a big deal. It looks mostly like something like this. Okay, that's pretty much what Nevada looks like, more or less. Not maybe right now. Right now it's in about 12 feet of snow. I don't know if you've heard about that. But at the Sierra Nevada mountains right near Reno, they got like 12 feet of snow. And it's pretty, it's kind of wild there right now. But usually that's what it looks like. And so going to Louisiana, it's way more biomass, so it's more exciting for me. Okay, who can name the plants? Who can name this one? Rice. Who said that? Oh. What's your name? Elsie. Thank you. Answering questions. All right, so who can name this one? Or no, this one. That's cotton. That's right. Who said it first? They did. Okay. Well, I don't know if I can get up there. Let's see if I. No, I better not throw it. We'll have to pass it down. There we go. Okay. So that is cotton. So when you get cotton off of plants, what do you think is left? It's actually called cotton gin trash. Okay, so that's what's left. For rice, what's left is rice husks. Okay, so that you have the rough rice game, you take off the husk. I work with the husk. Okay, can anybody guess what this is? No, it's not corn. It's actually sugar cane. Yeah, sugar cane. This is actually sugar cane here. It looks a little like corn, doesn't it? That's where you get, when you have your coffee in the morning, you put your sugar in there. That's where it comes from, mostly. I mean, there are some sugar beets, but that's usually more like in Idaho and other places. Okay, can anybody guess what this is? It's actually what coffee looks like growing. Yeah, that's what it looks like. It looks like you have these coffee cherries that are red like that, and then you strip off the outside, and you finally get to the seed inside, all right? And that's what you then roast in order to make your coffee, and you grind it, obviously. All right, so those are some of the different plants I work with. Here is my team from last winter. Just a picture of us. I right now have 5 graduate students, and I usually have about the same number of undergraduate students that work with them and help them. It's kind of nice for the undergraduates because they learn different lab skills, and it's nice for the graduate students because they have another pair of hands to help them with their work. So that's pretty much what I'm looking like. I have been funded by USDA from time to time. I'm presently funded by the Environmental Protection Agency to try to prevent pollution. All right, so that's kind of what it looks like. All right, so my team and I do research on waste biomass. And this is a picture of what I have in my offices. I actually have 2 different offices. It is the glory of God to conceal a matter, to search out a matter is the glory of kings. And that's Proverbs 25:2. And so I take that to mean that we who research are actually royalty, right? And if you think about it, hundreds of years ago, how likely would it be that you'd be able to spend time researching some topic? You'd be busy trying to make a living. Only people who are extremely wealthy could, take the time to actually do research. So I think that all of us who research are indeed royalty. Okay. All right. So I want to first talk about lignocellulosic biomass. So you have those things we saw. You harvest them. They're plants. They have cell walls. In the cell walls are macrofibrils. And the macrofibrils are microfibrils. That's supposed to be microfibril. Sorry about the typo. So what microfibrils are is they've got a bunch of cellulose in the middle. Who can point to some cellulose in this room? Well, wood is part cellulose. Pretty much pure cellulose. Is anybody taking notes? Who said it?
Dr. Hathaway said
Okay. All right. Well, you get a sticker as well. Okay. So who said it?
the man.
Okay, the man. There you go. You get a sticker too. You can put it on your laptop too. That's awesome. That's allowed. Okay. Right. Cellulose is paper. Have you ever driven past a paper plant? Maybe, yeah. They take wood usually softwood, and they get rid of the lignin. Okay, so this is lignin. How many of you have ever had chemistry class? Yes? Okay. Well, that is what the chemical structure of lignin looks like. It's a bunch of aromatic rings, and they are bonded 2 or 3 times, so they're like a big macromolecule. That's what lignin is. Paper plants get rid of the lignin. Lignin, however, in the natural state protects the cellulose. Now, cellulose is just a bunch of glucose molecules all lined up in a straight line, and they hydrogen bond together, and that's why they become crystalline. Okay? And there's also C5 and C6 sugars that are called hemicellulose that also protect the cellulose in a microfibril. So that's kind of what goes on. Paper plants take out the lignin, and they use the cellulose to make paper. Okay, so what do? I do the same sort of thing. I'm taking waste, pine needles, for example, or rice husks or other waste biomass, and I'm getting out the lignin and separating it from the cellulose and hemicellulose, which you can make biofuels from, or polymers. Bless you. Lignin you can also use. You saw all those nice aromatic rings, so you can turn it into platform chemicals, or you can just use it as a fuel. All right? Okay, so has anyone ever opened their car windows when they went past a paper plant? Okay, what did it smell like? Bad, right. Why do you think it smelled bad? Do you have any idea?
Bad chemicals.
Bad chemicals, yes. So basically, they use what's called the Kraft process, which is a very old process, and this has a lot of sulfur in it. And the sulfur dioxide and the sulfur compounds are what you are smelling when you smell that, okay? So that's kind of what the traditional way to do that kind of separation is, and so I am looking into greener and safer methods in order to do the separation of lignin from cellulose. So I use things called ionic liquids. They're basically salts that are molten at room temperature. I mean, your table salt, it's got a melting point of about 1,000, right? But these are different kinds of salts. They're very interesting. I also use what's called deep eutectic solvents, and I'll talk more about those later. And I also use what's called hydrothermal carbonization. Okay, so those are the kind of greener and safer methods I'm using in order to avoid volatile organic compounds, like the bad stuff you smell near paper mills. All right, so I'm going to talk about hydrothermal carbonization first. This is our PAR reactor I have in my lab. It's a little reactor, a little batch reactor. It's about 2 liters, and my students work with that. They basically just put waste biomass and water into it. You do it for about 5 minutes at those temperatures, so the water is compressed. Okay. How many of you, do you guys ever do thermodynamics? Anybody take that? Maybe not. Maybe a few of you, all right. So it's hot compressed water. And once you're done with that, you get organic acids out, you get aqueous sugars out, and you also get a solid fuel product that is mostly lignin. All right? So that's one way that I separate it. The reason it works is because this is the ionic product. In other words, how the water kind of turns into a positive and a negative ion at certain temperatures, around 200 degrees Celsius. All right? So you can see the ionic product's way high at those particular temperatures. Now this is only in liquid water. If it is steam, it's a totally different animal. Okay. The other thing that I did want to talk about, so we're taking this stuff. This is what rice husks look like when you get them. So I do deep eutectics or ionic liquids of that for the separation. I do HTC to get a solid fuel pellet. It also acts well as a binder for raw biomass. The other thing you can get on there is ash. So ash is basically inorganics. And we've tried putting this ash into cement. Okay, and I'll talk a little more about that later. This is just a slide I like to show because I think it's cool. This is what used to work a lot with raw loblolly pine. That's the typical pine you see off the roads. This is what it looks like. This is what it looks like after you have pre-treated it with that half an ionic liquid and half glycerol. Okay, you get essentially a pulp or a cotton-like texture out of it. So I like looking at things with scanning electron microscopy. This is what it looks like under the microscope. All right, this is what the raw loblolly pine looks like. If you pre-treat at the same temperatures, this would be around 160 degrees C. With glycerol, it kind of looks about the same, but if you do it with these ionic liquids mixed with glycerol, you get the wood cells to separate and get rid of the lignin. So that's how an ionic liquid can work. Okay. All right. Okay, so another way that I work with wastes is using direct contact membrane distillation. So basically you have a hydrophobic membrane, okay, and you have something that you want to get pure water out of it, okay? So often with ionic liquids they end up getting water in them when you use them. And so you want to reconcentrate them because ionic liquids are quite expensive. So and the nice thing about this particular direct contact membrane distillation is it only uses really low temperatures. So you could even use waste heat, and you can do it at ambient pressure. So this is kind of what it looks like, okay? You got a hot ionic liquid water solution here. This is a hydrophobic membrane. Do you think ionic liquid likes to go through hydrophobic stuff? Think hard. No, it does not. That's right. It doesn't want to because it is very hydrophilic. So it doesn't want to go through this membrane. But water vapors, they're small enough molecules that they can go through the membrane, and then they go up and are condensed in a cold water stream. So you get pure water out here, and you concentrate this so you can reuse it the next time. That's kind of the story with that. And this is just what that process looks like. And this is an actual picture of what our unit in our lab looks like. So that's the membrane. On the bottom we'd have the hot solution. On the top we'd have the cold water that we're trying to get pure water with. Okay. All right, and it just works because the more volatile a substance is, the more likely it is to be able to go through. Less volatile substances and more hydrophilic substances won't go through. So just the vapor pressure difference. All right, so I'm into secondary agricultural residues. Can anybody name a secondary agricultural residue? What is primary? What is secondary? What?
Corn husks.
Corn husks, yeah, that would be a secondary one. Because they go to the processing center, and then they take the husks off, and then they process the corn, right? That's good. Have you gotten one of these yet? No, you have not. Whoa. But he had a good, woo! You did a good job. So actually, primary agricultural residue would be like corn stalks. Because I don't normally take the stalks to a processing center, but they are a waste from corn production. But I'm really into these because you have to take if you have to ship something from the field to somewhere, it gets expensive if you're doing it for biomass. And the reason is because biomass is fluffy. You fill up a whole semi-truck, it only weighs a couple 100 pounds. But if the secondary agricultural residue is already there, then you don't have to ship it, so you're not wasting all that gas shipping this fluffy material. So anyway, I'm interested in rice husks or rice hulls. You can see that rice is the second most produced crop in the world after maize or corn. And the one weird thing about rice husks is that they're about 20% inorganics or ash. So it's kind of a weird biomass, actually. All right, deep eutectics. So I said I'd tell you about those. Basically what those are is if you take two different substances that have high melting points, so for example, choline chloride and urea, okay? If you have those two different things and you mix them together at just the right ratio of molecules or moles, then you get a way lower melting point, okay? And that's called the eutectic temperature. All right, and so the reason they're called deep is because this is kind of a deep valley. That's all that is. What happens on a molecular level is they sort of form a superlattice. And so that's why their melting point goes way down. Okay? So I've been working with those lately. Nice thing about those is they're not very volatile. They're not volatile organic compounds. They are compatible to water. Usually when you harvest the biomass in the field, there's a lot of water that you'd be surprised how much there is. Okay, they're non-flammable. They're biocompatible, at least the ones I use are, and they're biodegradable. And they can also dissolve lignin. So that's kind of the main selling points for deep eutectics. Okay, ionic liquids tend to be pretty expensive and hard to make. Deep eutectics, we make them in our lab all the time. Okay. All right, so here are some of the ones we've used. We use lactic acid. So that's the thing that hurts in your arm when you work out too hard in the gym. We use betaine, which is from beets. We use choline chloride, which is actually a vitamin for chickens. Makes them grow faster. Kind of cool. And acetic acid, which essentially is vinegar, right? Although vinegar is much more dilute than pure acetic acid. So those are the kind of deep eutectics I mostly use. Here's some biomass we have used deep eutectics on. We've used them on pine needles. You remember seeing that structure. You have lignin on the outside and hemicellulose, and you have cellulose in the middle. Deep eutectics will separate the mostly cellulose to mostly lignin. Okay. Let's see. All right, and okay. So another one that I showed you, the coffee cherries. After you get the cherries and you take off the outside part and you get to the seed, this is what coffee beans look like before they're roasted. And then you roast them. If you roast them a very short period of time, you get a blonde roast. Has anybody ever seen one of those at Starbucks? If you roast them for a medium length of time, you get a medium roast. And if you roast them for a long time, you get a dark roast. So which has the most caffeine, do you think?
Blonde roast.
Blonde roast, right. That's because you haven't roasted up or degraded the caffeine in it. So I have blonde roast when I make my coffee in the morning. I tell you, I need it. Anyway, but when you roast it in the roasting oven, you end up with something called coffee chaff, also known as silver skins, okay? It's like a little tiny piece of parchment paper that comes off the bean that's like an outer coating for it, all right? And so you have this stuff, it's kind of fluffy, it flies all around the place you're roasting. I've heard that Folgers spends about $70,000 a year just getting rid of coffee chaff, taking it to a landfill, right? So I was like, well, what can we do with that? So basically what we did with that is this same sort of process. We dissolved it in a deep eutectic solvent. We got a sugar on one side, we got lignin on the other. This can be made into fuel pellet. This you can ferment to make into ethanol. I've also done it obviously with sugarcane and with rice husks. So this is sugarcane bagasse. Now what bagasse is after you squeeze all the sugar out of your sugarcane, it's what's left over. All right, so there are big piles of bagasse sitting all over the state of Louisiana, but you can use it in order to do the separation get sugar, which you could ferment, and get lignin, which you can turn into a pellet and make into a biofuel. All right, let's see. And this is, I was talking about rice husks and how they have a lot of inorganics in them. If you burn them, you can get energy out of them. You then have a bunch of ash, and you can put it into cement, and you can make the cement actually stronger. All right. So let's see. I'm gonna pass around. So we do that. We work a lot with cement actually in our lab, putting different things into it that are waste products. So I'm gonna go ahead and pass this around. Maybe we'll start in the back. There you go. So that's the kind of mold we use to put our cement in, and then we cure it or let it sit for 28 days, and then we do compression testing on it to see how that goes. All right, so let's see. I think we'll go on to the next one. We only have a little bit more time. Where'd it go? Oh, there it is. Whoop. There must have been another screen. We'll put that one down. Put this one up. Okay, so this is just kind of interesting stuff. Waste we have worked with. Oh, do I have to do slideshow? Let's see, let's try that. It work? Yes, it did. All right, very good. Okay, so we have worked with a lot of different waste actually, at different times. So you've probably seen things that were galvanized. I suspect this probably was galvanized, but basically you're dipping your metal into a sulfuric acid solution and then pulling it up to make it perfectly straight, polished. It's called electropolishing often. But it's got sulfuric acid. So one company, what were they going to do with our sulfuric acid once they couldn't use it for galvanizing anymore? Well, normally they used to just dump it down into the sewer. That's not so good. So now they have to pay more for hazardous waste disposal. And so we said, oh, what could we do with that? And so we got the spent sulfuric acid, and we got what's called black liquor from a paper plant. Okay, and that is essentially lignin, but the problem is that it is dilute and it also is a very high pH. So if we combine an acid and something that's high pH, what do we get? Neutral. Neutral, yes, that's right. And so we get neutral lignin out of that. So we took that, and we also got some steel waste. All right, this is called red dust. Okay, and so we got this waste from steel mills. We combined these two things. So, and then we also combined with that some geopolymer reactants. Now, what's geopolymer? Basically, it's sodium silicate plus sodium hydroxide. Okay, and if you combine those two, you get something that's a little bit like cement. So we put that in there too, and we made this briquette, which then we could again use to help in the steel making process. Okay, so that's kind of what we've been doing. We've also done stuff putting wastewater from paint production into cement. Let's see what else. We've done oil spill cleanup. So basically we took sugarcane bagasse or rice husks, and we've made them into ash, and then we've combined the red dust from the steel mill with that, put it on a magnet, and we made it so that it would soak up oil. So we were simulating an oil spill. All right. And then when you change the polarity on your electromagnet, the oil would come down, and you could get rid of that and use it in a geopolymer. So that's just another thing we've done. That's the actual chemistry stuff going on there with that. We've used lignin that we've gotten out of stuff to help with subgrade soil. How many of you have ever seen long cracks on the edges of a road? You probably have. The reason for that is the subgrade soil absorbs too much moisture and then gives it up. And so it's going up and down, and that's making cracks happen in the asphalt. And so if you add lignin to that sort of soil, some of that expansive soil, you can stabilize it and you get less cracking. So that's one thing we've done with lignin. Okay, well, we're going to go on to some of this NASA work that I've done through La Space, which is the Louisiana's NASA group. And so we are interested in, if you're going to the moon, you're staying there a long time, you're going to have to go. And so astronauts are going to be up there, and they're going to have to pee, all right? And so we decide, well, could we concentrate that urine and make it into a cement plasticizer that you could make with moon dust or regolith, okay, to replace the ordinary Portland cement. And so we decided to use artificial urine. We didn't really want to ask for donations. And so we did that, and we found out that, yes, indeed, you could get pure water out, which on a lunar base, you're going to need pure water. That's going to be a problem, right? And then you can also use this concentrated urea, mostly, as a cement plasticizer. So that's one thing we've done. Okay, this is kind of what it looks like. This is the urea water solution. That's the cold water, and you can use it for a plant. So a similar sort of thing. We're also looking at aquaculture. How is aquaculture different than hydroculture or hydroponics? Anybody know? Aquaculture usually has a fish component, whereas hydroponics doesn't usually have that. So we're thinking about taking the fish wastewater, concentrating it, and using it as a plant fertilizer. And then we can take the pure water we get out of that and give it back to the fish. Okay, so that's one thing we're doing. All right, and here's the last one. We have gotten lion manure from the New Orleans Zoo. All right, and we did hydrothermal carbonization of it, and then we pressed it into pellets, and here I am dropping it 1 story to see how durable the pellet is. Okay, and the pellet was very durable. Nothing broke off when I dropped it. So this is just a picture of one of our labs at Louisiana Tech for chemical engineers. You can kind of see the distillation column at the one side. This is the lobby area where students mostly just hang out. This is some of the different units that we use. So that's where that is. All right. Nope, we're not quite done yet. I want to do one more. We still have a couple minutes. So let's pull up the last one. And we'll do this one. Okay. Okay. So I do want to talk to you guys about graduate programs at Louisiana Tech University. We are a well-known, well-established, accredited chemical engineering program. You can see this is what the campus looks like. This is our ivory tower, right there. This is we have a new engineering building right here. That just started about 2 years ago. It got built. But basically, there's a lot of research that goes on at our place. We have what's called the Institute for Micromanufacturing, which I'm part of, and it has its own separate facility, but it's part of the campus. I am also involved in the MALT Industrial Assessment Center, which is basically we go to companies and we say, how can we help you save money? We go there, we look and see, okay, do they have fluorescent lights or do they have LED lights? That's one thing we look at. Because the payback period to replace fluorescent lights with LED lights is very short, like 1 year. And then they've got these nice, LED lights that don't give out, essentially, compared to fluorescent bulbs. We go there, and I go there, and I find any waste they have and see, gee, can I turn this into a product for them, or is there a way I can help them reuse this or recycle this? All right, so that's what MALT does. We drive all around. We could even drive here. We could even do it in Texas. That's what MALT actually stands for: Mississippi, Alabama, Louisiana, Texas. So we do all those states with our Industrial Assessment Center, and we've saved lots of money for a lot of companies. All right, so there's a master's program in chemical engineering. It'll probably take you about 3 years. You can either do thesis, where you write a thesis, or you can do what's called a practicum, which is, if you don't like writing, you just write a report. It's not as hard to do, but you have to take a few more coursework things with a practicum. And these are some of my master's students that have been graduating lately with me. And typically, if you are a U.S. citizen, you can get funded for these sorts of things. It's a little harder if you're a master's student from another country, but if you're from this country, usually you can get funding to do it. And then we also have a PhD program. It's called a PhD in engineering, and it is micro and nanoscale systems concentration is the typical one that people do in my lab. One guy is doing the materials concentration. You get to choose which concentration you want. And this is a little bit closer to chemistry, this particular concentration, than many concentrations. And it takes about 4 or 5 years, just depending on how fast you work on your research. And again, as a PhD student, you get funded for these things. And here's one that I've graduated and one that's working in the lab with my power reactor right there. So that's kind of what that looks like. Whoop. Let's go back to this guy. Yep. Somehow I decided it wanted to. Okay. Actually, I'm missing some in that one. Let me get rid of that one. I need to find the other one. Okay. There we go. All right. Didn't start yet. Okay. Okay. So that's the same slide. I thought I changed it. Oh, whatever. Okay. So I want you to thank you for listening, and I want to find out if anybody has questions for me.
Over here. Question.
Oh, there you are. Okay, yes.
So in your applications of like biomass conversion, the last you mentioned was lion manure and how you like compress it into a pellet to test its durability. What would be the application of doing that? Like, how could you use that as like
A fuel pellet.
be a fuel pellet?
Yeah.
Okay.
There's probably things at the zoo that they need to heat up or dry or something. You could just use it as a fuel pellet.
Okay.
The thing about lions is that they eat mostly meat. And so the other thing that hydrothermal carbonization does is it essentially sterilizes it. So you wouldn't be dangerous to work with after you've done that to it. It wouldn't have like microbes and so on from eating and stuff. Yes?
A lot of the applications you mentioned were for energy conversion or production, perhaps for solid fuel or liquid fuel. And my question is, it would seem that the transport energy and the conversion energy and the waste heat caused by it, the energy needed to make your chemicals to do the conversion, all of that energy put into this process would be greater than what comes out of the conversion. So not even speaking about price and cost effectiveness, but just energy in being greater than energy out. Is that something that your research focuses on, or is it more about preventing waste, or is it more about actually being profitable energy-wise with how you convert it?
That's a good question. Let's give him a hand. Woo! Yeah. Reach it. All right. Yeah. So that is a concern. That has been a concern with making, for example, corn stover, the leaves and stalks of corn that are left in the field. There's some conversion. Is this going to be carbon neutral or not? And that is a good question. It depends what you're comparing it to, and whether you're more interested in how much CO2 is going into the atmosphere compared to how much money you're making. All right. So, for example, all biomass is pretty much carbon neutral now because it takes in carbon dioxide before it is burned or whatever. Personally, I like to see things turned into products that are not fuels necessarily. The thing about things like rice husks is if you're just going to put them into a landfill, you're kind of wasting all of that energy that you have. Now maybe it takes, actually I did do a study on rice husks and putting them into cement, okay, which is not a biofuel, which you're talking about. We'd rather not have the waste biomass get burned, but if you can burn it and get the energy out of that, and then you can get the ash and you can put it in the cement, you're replacing the cement that would normally be mined and then made. And ordinary Portland cement is a very, very energy intensive process. So I actually did that study. Actually, I do have the paper for that. We did publish it. Proving that if you use rice husk ash, you would be using less energy and less carbon dioxide would be going in the atmosphere. Just because ordinary Portland cement is so energy intensive to produce. You have to mine the materials, you have to heat it up to extremely high temperatures, you have to grind it. So when you go down to Lowe's and you grab a bag of cement, there's a lot of energy involved in making that. Right. So I'm really a little more excited about using materials that would be wasted otherwise into other products like cement, rather than just turning them into a biofuel. But your point is well taken, yeah.
On a similar note, you said that on one of them you used it was the rice husk or the corn stuff, or no, the cane,
sugar cane bagasse, yeah.
Yeah, that stuff. To separate oil and water and turn the oil into, the picture shows a magnetic clump.
Yeah,
how does that work?
It's kind of a weird process. Part of it is because you're using red dust from the steel industry, which is ferromagnetic, and so it's sort of, and you have to put this other stuff on it. It's pretty complicated, but it will absorb the oil, and then you can lift it out, and then if you change the polarity of the battery, it'll drop the oil down. So it's a very preliminary study, though. So I don't know if it would really work or not, but I think it might. We've published on it. So
would it turn the oil into like a ferroliquid, or?
No, you stick the red dust and the sugarcane bagasse ash, and there's another chemical which I forget. It's up there somewhere. Anyway, you stick those on there, and that part doesn't come off. The oil just absorbs on, and then it drops off when you change the polarity. I don't know. It's not well explained. I could send you the article if you really want. You don't care that much. Maybe just a little.
Just a little.
You send me an email.
Okay.
I'll send you the article. Yes.
Okay. Thank you.
So, when you're making cement out of these like rice husks and stuff, do you make enough to where it's like, oh, we just don't waste it, or do you make enough to where it's actually like potentially replaceable for the cement ways we have now?
It is very replaceable. We've gone up to 20 or 30% being rice husk ash, and it works perfectly fine. The reason for that is because rice husk ash in particular is very high in sodium dioxide or sand or whatever. It's very pure stuff compared to some other ones like sugarcane bagasse ash. It's only 70% silica, so it's not quite as good. But rice husks they're very pure stuff. So it's kind of cool. Yeah.
So I was kind of curious why you
I'm not sure. So you're talking about the lion and the giraffe?
Yeah, like they're
Okay. So why not do a plant-based one? Plant-based animals manure tends to be less having microbes in it. Okay, and so it's less dangerous than something that just eats meat. And the hydrothermal carbonation process actually sterilizes the material. So if you for example, people have used buffalo manure for a long time, right? You just let it dry and you're fine. And that's because buffalo eat grass. So it's not really very dangerous stuff. But if you're talking about lions or cats and anything that's totally meat-eating, kind of dangerous. So that's kind of why we were more interested in that. But yeah, good question. Oh, you need a sticker too. Good question. Okay.
You were talking about how the red dust on the fuel processes. How abundant is red dust? Is it a byproduct of
It's a byproduct of steel manufacturing, yes.
steel manufacturing, also like incredibly toxic? So would that become like a necessary material to your process, so that you have to manufacture?
Well, the fact that it's a waste and normally they throw it out, that's why we're interested in it. So, can you get a sticker?
Oh, I've done once.
Okay. Good question, yes.
Is the red dust chemically identical to iron oxide that could be found in nature?
Probably,
And if so,
yes.
have you considered using that?
Well, that's not a waste product.
It is, it's sitting outside, so is a landfill. What's the difference?
They have to transport it to the landfill. You know, yeah, I mean, you can dig up iron, I mean, for sure.
Okay.
There's no, but mining is an energy-intensive process itself.
Okay, so that's the difference. You have it already in powdered form.
And it's already at the site,
Yeah. Okay. That makes
all
sense.
ready to go. So, but wow, you're really getting me. That's good. You're doing well. Okay, other questions? I think we have to leave. One more question here.
So you mentioned your malts team that goes around and helps companies and stuff. I was wondering if they come to you or if you look for specific things that you've done that you can help them with, and if any of those have been really big success stories that you wanted to share.
Oh, I'm trying to think what we've done a lot of them. I'm trying to think of one that would be particularly good. Usually they come to us. They hear that this center is here and they're like, yes, we want to know about it. And so I think, yeah, the ones we've gone to, they've been looking for us. I think we've just got the ones that were like super eager, oh, we got to do it, to the ones that are like, okay, yeah, we'll do that, you know, so. Anyway. Okay, well, it is time for us to let you go. But I want to thank you all for being such a great audience. Woo!
Dr. Lynam will be here for a few minutes, and then we'll be in the Joyce Room of the Corner Cafe if you want to join us for lunch. And if you don't have a meal plan, I can buy you lunch, so don't let that stop. All right, see you all in 2 weeks from today.
Okay, that's usually just bioethanol. Please tell me right now. Good, thank you, sir.